Today, the master class will be about a specific type of DC to DC converters, which will be step-down DC to DC converters, aka buck converters. My friend Yousef and I will deliver today's master class. Just to briefly introduce ourselves, I'm Hakan, co-president and electronics team advisor, and Yousef is one of our brilliant members in electronics team. So let's start with a recap from the previous master class. In the previous masterclass, we have talked about two prominent features of DC to DC converters. Those features are high efficiency and high control. To obtain high efficiency, there are two important components that should be used in DC to DC converters, which are high frequency switch and energy storage buffer. The use of these two important components is leading us to the specific concept of DC to DC converters, which is step-down DC to DC converters. Now let's have a look at the logic behind this, behind the step-down DC to DC converters working principle. The circuit diagram on the slide is the rough illustration, which includes prominent circuit components which help the converter to attain two aforementioned key features. Vin is the energy pulses drawn from the power source here. We obtain the control of energy flow in converter by changing the time of the switch. You can see the switch here. Also, filter is used for the energy storage buffer. And VO on the right hand side is the smooth voltage applied to the load. Now let's elaborate this basic circuit model and delve into the functionalities of each key component used in the step-down DC-DC converter circuit, which can be seen on the slide here. So power MOSFET is used as, you can see power MOSFET here. Power MOSFET is used as high frequency switch. The inductor next to transistor MOSFET, I mean, is used as the energy storage buffer. The freewheel diode here is used to direct the current flow when the MOSFET is off, and the capacitor is placed in parallel, as you can see here, to ensure and check the smooth voltage, which is VO, which is mentioned in the previous slide. So we have some key assumptions for an ideal step-down DC to DC converter. We assume that the components are power lossless, and we assume that the converter has virtually ripple-free output voltage. Also, we assume that the inductor current is continuous. However, unfortunately, in real life, the things do not work as assumed in the ideal conditions. Now let's have a look at how the current flows when the transistor is on and off. When the transistor is on, in other words, when the when the switch is closed, the current flows the current flows in the path which is indicated by the red arrows on the slides. So the freewheel diode is reverse biased, since it is told in the previous slides that the diode is placed to create a path for the current, but when the transistor is off. But here we are considering the condition when the transistor is on. So when the transistor is off, in other words, when the switch is open, it will not be possible to get energy pulses from the power source outside, because the switch is open. So, however, the energy stored by the inductor here will keep the current flow consistent during the operation time. Simply in this case, the inductor keeps the power flow consistent in the circuit. You can see the path in which the current flows on the slide, indicated with the red arrows again. it moves in clockwise direction. So before going further analysis, there are some important definitions that you should know. T will be used in the further slides and further calculations, and T is a transistor switching period. And D will also be used and have a key role in further analysis. And D is the duty cycle, and the duty cycle is the time when the transistor is on, which means on time of the transistor, divided by the period T. Also, I mean, the duty cycle is a value which is between generally, I mean, like always, not generally, is between 0 and 1. Now, my friend Yousef will take over my place to continue the class, starting with the further analysis of step-down DC to DC converters. Floor is yours, Yousef.
In the circuit shown, we analyze the circuit as we can see from the figure. When the transistor is on, the voltage, the voltage on the inductor, we analyze the inductor voltage and the inductor current in this figure. So the voltage on the inductor is the input voltage minus the output voltage. And what that does to us is, since the derivative for the current is a positive constant of V input minus V output, the current increases linearly according to the current equation of the inductor. And when the transistor is off, the circuit will diverge to the current will divert to the freewheel diode, and the output voltage, as we said, if we neglect the voltage of the diode, it becomes voltage output equals voltage. The voltage on the inductor is minus the voltage on the of the output, which we can see in the figure of the inductor voltage. And that means we get the inductor current will have a negative derivative, which gives us a decrease linearly. And the decrease, next slide. And for this, the increase, the linear increase in the current in the first cycle and in the second cycle must be equal to each other. That's because the inductor current and at the end of the switching cycle must be the same in the steady state operation, of course, over one period, which needs to be 0. The current rise plus the current fall must be 0 in one period. And that gives us the equation on the bottom, which is V output equals the duty cycle multiplied by the voltage input. Next, please. As we've seen, the duty cycle is managed by the transistor, by the MOSFET. It's managed by the driver circuit of the transistor, the input, and the frequency of switching, the switching frequency of the transistor, which is managed by the driver circuit of the MOSFET transistor. And when the duty cycle is equal to 0, the voltage output would be 0. That's logical, because the transistor would be an open circuit and there is no voltage input. And when the duty cycle is equal to 1, and that means that the transistor is always conducting, which means that it's basically no use for it. And the important thing about this on this slide is that the voltage output is independent of load level when using a resistor load, of course. When using an RLE source with resistance, inductance, and electromotive force, that's another story. And sometimes it will affect the circuit, but we always try our best to make the output voltage independent of the load. Next, please. here we analyze how the current for the capacitance work. When the capacitor current is positive, the capacitor is charging, as we can see in the bottom figure. The current of the capacitor is charging, and therefore we it starts charging. That's because the current is positive in the inductor, and that the total current is positive. So the capacitor starts charging, and according to the definition of the capacitance. And as we can see from the figure, the current of the inductor is a DC current with some harmonics, but it's a DC current with some not harmonics. It is a ripple with a ripple current, as we can see, delta current of inductor, and the current of the capacitor is AC current. As we can see, there is oscillation around the x-axis, which is time. Next slide, please. And as we can see from the capacitor current, the area over one period is 0, which is the area of one period is the DC component according to Fourier series, and that shows us that there is no DC component in the capacitor current. Next slide, please. In this last slide, we see how the ripple of the output voltage is affected by the capacitance, the period of which the period of the transistor, which is basically like the frequency of switching, and the ripple of the inductor current. And therefore, there will always be some oscillation in the output voltage, unless we try to minimize it as much as we can, since as we can see here, and the positive, when the capacitor current is positive, it's charging, the capacitor is charging charges, and the voltage output increase slightly. And when the inductor current and the capacitor current is negative, the charges is decharging, so the voltage output is decreasing slightly. And how we can reduce this ripple, which is done by doing higher frequency switching by using the transistor. And that's how we get, instead of using big capacitors, which is really not feasible, we just use higher frequency switching using better switches, which is better transistor and a higher frequency transistor. And that is all done using a very high controllable transistor, using the driver circuit.